My screen is visible to all of you, students.
Yes,
Yes,
sir.
sir.
So, we have seen this first unit. We are dealing with the simple stress and strain. In this, we will discuss various concept of stresses and strains, Poisson's ratio, and we will try to solve some numericals related to the temperature stresses, strain, energy, Moore's circle, generalized Hooke's law. All this we will try to cover in this first unit. Books which you have to refer, I have already mentioned in my presentation. You will get maximum books in our library also. You can access those books. And the topics which we are going to cover, I have already briefed. So, stresses. Let us start with stress. Stress, I am abbreviating it by rho, and stress is equal to load per unit area. Load per unit area. I am abbreviating load by P. Load per unit area is stress. This load may be in kilonewtons or newtons or kg or pound or gram. Area may be in meter, centimeter, inch. So load divided by area, you will get stress. I am abbreviating strain by epsilon. And various types of strain we will see later on. But currently here I am giving you how to calculate linear strain. Linear strain you can calculate using this change in length, which I am abbreviating by delta L upon original length. So this strain, whether your length you are calculating, you are measuring in meters or centimeters, whatever it is, strain will be your unitless parameter. It will not have any units, and stresses will have units, load per unit area. So moving further, various types of loads. In this, it is clear that axial load is acting. In this figure, the axial load is, we can call it as pull load. It is pulling the rod and the length is increasing. In this second figure, this axial load is acting in a compressive manner where the length is going to be decreased. In this case, definitely pull is there, so length will increase. Here, the decrease in length will be there because the force is compressive in nature. So, change in length, if we assume that whether it is a pull or it is a compressive axial force, if change in length is delta L, then either strain can be calculated as change in length upon original length. If it is a pull, means the length has increased by delta L, and if the length is decreasing in case of compressive load, you can calculate strain as delta L upon L, same thing, but you can use negative sign. This negative sign will indicate that the length has shortened, but the magnitude will be same and the units will not be there. Strain is a unitless parameter. Moving further, this is the example here pull is there. Because of this pull, this rod has broken into two pieces. These stresses are developed at the surface of the failure. They are shown like this. So these are the stresses, and these stresses can be calculated as P divided by this area A. If it is circular in section, area can be calculated pi by 4 into dia square. If it is rectangular in section, area can be calculated as width into depth. So this is the diagram or figure, or you can call it as free body diagram, showing the stresses developed because of this axial pull on this rod. Now let us switch over to Hooke's law. You might have studied in 12th standard stress up to certain limit when ductile material or a rod made up of ductile material is subjected to axial pull, increase in length will be there. So up to certain extent, stress will be directly proportional to strain, and stress is function of load. So if you will try to plot graph, and if a rod is subjected, suppose this is circular rod I am considering, if this circular rod is subjected to axial pull, which I am abbreviating by P, then definitely this rod and suppose the length is L and the diameter of this rod is suppose D. Because of this load, definitely this rod will be pulled, and initially stresses developed because of this load, because stress is a function of load. So because of these stresses, because of these loads, stresses will be developed, and because of the stresses, this rod will get broken into pieces. So initially, if you will try to plot the stress developed versus strain, you will get straight line. This straight line indicates that stress is directly proportional to strain. If you will calculate the slope of this straight line, which I am abbreviating it as theta, then obviously theta will be equal to slope will be equal to y upon x, right? So if you are using tan theta here, right? If you are using tan theta here, you will get here strain, you will get here stress. So intermediate values, if you are choosing to calculate this slope theta, then for small angles tan theta is equal to theta. So you will get strain upon stress. If you are trying to plot the same graph in this way, putting strain as abscissa and stress on ordinate, you will again get straight line. If you will try to evaluate the slope, then tan theta here will be equal to perpendicular upon base, that is stress upon strain. So this slope of a line, when it is following the principle that stress is directly proportional to strain, you will get slope theta, and the slope theta we define it as modulus of elasticity. So modulus of elasticity is equal to stress upon strain. Now one exercise I am giving to all of you, that in universal testing machine, if you will put a rod made up of ductile material and you will apply pull, you will note down the pull and the area and the elongation in length with the help of strain gauge. You will definitely get the values of stresses and corresponding strain. You will plot the graph. You plot like this and you try to plot like this. Then you just watch and see the difference, what you will get. This is the exercise for all of you, but in books, in textbooks, you will get this. Strain values are plotted on x-axis, stress values are plotted on y-axis. If you will try to evaluate the slope, it is not compulsory, you can choose any value. Like you can choose this value, you can choose this value. Any value you choose, you will get slope tan of theta. And the slope of this straight line will be stress upon strain. And this ratio of stress upon strain is known as Young's modulus of elasticity. So this is, you will get in all the books, but this is the exercise in laboratory you have to do. You try to plot like this. Let us see what you will get. I am giving you hints. Either you will get like this or you may get like this. What you will get, please check. And when you will try to determine the slope of this black color line, and if I am abbreviating it as theta, so tan theta will be again here perpendicular, that is stress upon strain. So if you reverse the exercise, the assignment to you which you have to perform in laboratory is, if you reverse the plotting of the values of stress and strain like this or like this, how you are getting a straight line, how you are calculating or evaluating the slope is the question. Generally in textbooks you will get like this, wherein you have to plot strain on x-axis, stress on y-axis, and you are calculating the slope, and whatever the slope you are getting, that is modulus of elasticity, stress upon strain. But remember one thing in this, that whatever you have calculated, this modulus of elasticity, I can call it as the function